Okay, so let's take it out for a spin, and I think you'll find it's pretty straightforward. My first one, let me just do it conceptual, okay? So not any numbers, but let's just talk through a situation conceptually, kind of the thing that you might see on the multiple choice question or something like that. Let's say I have two identical projectiles of some kind. I'll label them A and B for labeling purposes. So we have two identical masses. They're both dropped from rest. But the difference, of course, is that I dropped them from different heights. And so we already know, for instance, that if A impacts the ground with this speed, that's B final A, is B going to hit the ground going faster or slower, meters per second? Faster, right? It has a faster impact speed. So that's something that we could, well, I mean, that's probably already knew that from everyday life, okay? But in the old stuff, the kinematic stuff, the kinematics explanation for why that is, why is it that B impacts faster, is that, of course, they have the same acceleration. They both are accelerated, of course, 9.8 meters per second squared. But B has more distance and therefore more time to spend with it. Therefore, B impacts faster. You guys know the three dots, therefore? The math thing? Okay. So that was would be how we explained why is it that B impacts faster than A in the old reasoning. Let me show you how far we've come in this reinterpretation of the situation and explain why, energetically, how we can get that same result. So in the energy picture, they both start at rest, which means that both of them have no kinetic energy to start with. There's no energy in their motion. However, they do both have energy that is stored. And they have energy that's stored because you're above the ground. I would typically set H equals 0 down here at ground level because, of course, that's the end of the road in this problem. So they both have stored energy, but not the same amount of stored energy. Because remember, it's dependent on height. So this one is not as high above the ground. It has a little bit. This one has a lot more. So the amount of energy that is trapped in storage is not the same. And so, of course, we can tally these and find that the energies that they both have to start with overall are not the same. Ball B has far more energy. You just can't tell because it's all trapped up in storage. But you will be able to tell when it comes out of storage, and you can actually see it being manifested. So when this thing falls, gravity does positive work. And what that does is it transfers it from the stored form into the form you can see, kinetic energy. And at the end, the potential energy is 0 because we're at 0 height. Now the energy is still the same. The total energy is still the same. But it has been transferred from the energy form that you can't see into kinetic energy, which you can see. That's exactly what happens with over here as well. But of course, the difference is you'll have more kinetic energy because you had more potential energy to start. So that energy is also conserved. So the total energy is conserved, but you had more of it in ball B than you had in ball A. And so the larger potential energy that ball B had now comes out as a larger kinetic energy of it on impact. So in the energy picture, what we say is that they have the same, is that the potential energy of B is greater than that of A initially because it has it, because of the height, HB is greater than HA. And if the potential energy amounts aren't equal at the beginning, that the kinetic energy amounts will not be the same at the end. Which means that, therefore, B final B is B final A. So we come up with exactly the same result. Okay? We find for different conceptual reasonings, of course, that why is it that ball B impacts faster? Okay? Now, as far as how to actually calculate this, all we would do is say that this has to be equal to this, right? So we'd say that, let's follow along with the structure here. We'd say KE initial plus PE initial equals KE final plus PE final. We said that this was 0 because we dropped it from rest. It has no kinetic energy to start with. We said that this is 0 at the end because we set the final height to be 0. So what we basically have is that the energy that used to be potential at the beginning becomes kinetic energy at the end. We put in the formulas. Like so. The mass cancels, which is reassuring because you didn't need to know the mass to do this problem with kinematics. You shouldn't need to know it now. That would be weird. Right? We knew everything accelerated the same, so we didn't need to necessarily know its mass. And you can calculate that the final impact speed is like this. And you can indeed see that as H initial increases, B final increases. Which is to say, if you drop it from a larger height, it will hit faster. It actually turns out to be a square root proportionality. So you would have to quadruple the height before the impact speed would double. Hopefully you can see that from proportionalities. Does that seem easier than kinematics? I think so. I didn't have to set an axis. That was cool, right? I didn't have to set a positive and have to decide what was positive and negative and all that stuff. Didn't have to set up my 5 variables with required 3 things. Pick which one of the 5 equations. I think this is easier. Okay. And by the way, it works even if the acceleration isn't constant. So it's very powerful and very easy. I think it'll probably become one of your favorite methods to use. You'll use it whenever you can. It has one downfall, though. The one downfall is that nowhere does it mention time. So that's your dead giveaway. If you're asked to calculate the time it takes for something to happen, you can't use this method. It's the one thing you give up for all that you gain. If you're asked for the time that something takes to happen, you have to use the forces method. Okay? So that's the one thing we sacrifice here for all the problem-solving power that we gain from this. And what I'm about to show you is 2 more examples. The next one will really see the time saving, the being able to do problems more quickly is really the case. Now, this one, as you know, it's not that hard. It's only a couple lines with old stuff. But let me show you a problem where we can greatly reduce how quickly we can do the calculation with the energy method. That'll be the next example. So we'll see it as a calculating things we could do before, but more quickly. And then the final example I'll do is something that is way complicated that we could not have ever hoped to do it before, and now we can still do it. So the energy method will help us do things more quickly, calculate things we can do in other ways, but more quickly and more easily. And then it'll also help us tackle very complicated problems we couldn't have even touched before. So that's kind of where we're going with this. Let me do those two examples, and then we'll go back. We obviously have, I mentioned it was the energy method so far, so we're going to need to put some modifications on it as well to account for more things. Okay, any questions before I do another example? Yeah?
You said use the forces method with priming and kinematics?
Right, so kinematics is just description of motion. So forces help you find acceleration. Acceleration can be used in the kinematics
I guess
stuff.
I was calling like the FNet stuff in a different...
So that's the force method. Kinematics is a word that just means description of motion. So it does not include Newton's laws, which tell us the y of the motion, right? So here are your methods so far. So there's the forces method, which is Newton's second law and your kinematic stuff, right? So that's just your equations and stuff. You have what's called the work method. That's at the end of your homework number 6, the one you're working on right now, where the strategy is that you are thinking of your energy forms. You're only thinking of one energy form that's called kinetic energy, and you're looking at everything transactionally based on energy that's coming in and energy that's going out by this process called work. So what you do in these problems is you do the net work 1 plus work 2 plus ... and that changes your overall balance. So that's called the work method. That's kind of, I wanted you to get some practice with that before I unleash the energy method on you, because most of the problems at the end of homework 6 can be done with the energy method. Because we'll find that learning how to compute a work is not wasted. We're going to find that there's a role for it still in the energy method. Because while I've kind of maintained that the work is kind of happening in the background, and you don't really have to compute work explicitly, that's only true so far. So they'll come back. Time learning how to compute a work is well spent. Then the next method is the energy method. And the energy method just relies on finding these conserved quantities. So it relies on acknowledging that there are other forms of energy besides kinetic energy, and if you include those in your calculation, you can find constants. So it's just, instead of just kinetic energy, there's potential energy, and they trade, but the total is constant. So what ends up being your major methods in the class are the force method. You found those annoying, I'm sure, because there's all these components to worry about, all these plus and minuses to set. You have to set this scaffolding of what's plus x and what's plus y before you can do much of anything. But being that you have to contend with vectors, at least you can find the time it takes to do things. The other method is the energy method. Really, the work method is kind of a stepping stone for getting there. We'll basically take aspects of the work method and put them into the energy method, even though it may not seem like it right now. Of course, work is not really mentioned anywhere in the calculations. We'll find that's not the case for too long. This is nice because here we're dealing with scalars, numbers, whereas here we're dealing with vectors. So it's simultaneously easier to work with because it's just a bunch of numbers, balances of bank accounts, energy bank accounts, instead of having to deal with vectors. But we can't solve for time. Can't find the time to do anything. These are the major methods in the class for mechanics. I guess I'll include one more coming up soon called the momentum method. P vector is momentum. And you can see it is a vector. So our work with vectors is not done. We're not leaving them in hindsight. You still have to be able to do that, be able to break a vector into components and stuff like that. It's a vital skill. If you don't get the hang of it, it's going to haunt you for the duration of the entire physics sequence. Okay? These are your major methods in mechanics. Okay? This is kind of an overview. I'll put a star here, and I won't tell you yet anything about that, but there are certain times where you might want to use that. Okay, let me go ahead. Any other questions before I move forward? Okay, so let's do another example. This one, I'll actually give you some numbers for once. Here's my problem. I have an inclined plane. I'm going to let an object go at the top. I'm going to let it go at rests. Let me say that the angle is 30 degrees. I'm also going to have to say that the incline is frictionless. Friction is one of the major things missing right now from the energy method. So one of the very next things I'm going to do after this series of examples is get friction back in there. Let me say that the distance that this thing slides down the incline is 6 meters. And what I'm going to ask for is how fast is it sliding when it reaches the bottom. So again, this is a problem that you could have done before. In fact, it was I think it was on your homework 4 on the inclined plane problem. So let me briefly talk you through it. I don't want to write it all down, but this should be old hat at this point. You have two forces, right? Normal force and gravity. Normal force cancels off the component of gravity. Mg cosine theta, mg sine theta ends up being parallel downhill. Mg sine theta is the net force. G sine theta will be the acceleration. Just divided by mass. There you have your acceleration. Acceleration is g sine theta. You have your initial velocity, 0. You have your displacement, 6 meters. There's your three required things. Right into the constant acceleration equations. Out comes the final speed, right? Does that all sound good? Okay, so good old force method. Get the acceleration, throw it in there into your 5 equations. All right, let's go ahead and go with the energy method. Now the first thing you might point out is, wait a minute. Right now the energy method only accounts for gravity, but there is also another force in this problem, normal force, right? So where do I get off using the method in its current incarnation when there's another force? Why am I able to just get the normal force, throw it in for free? What's the work that it does? What is it? 0. The normal force does 0 work because it's always perpendicular to the motion. So the work done by the normal force is 0 because the normal force is perpendicular to the displacement at all times. I like to call the normal force a guiding force. The force is certainly not 0. If the force were 0, this thing would fall straight down. It would not consent to sliding on that diagonal. But the normal force will just guide the path on this diagonal line But because it will never have a component with the motion, it will never make it go faster. It never has a component against the motion, so it can't make it go slower. The only reason why this thing speeds up is because of gravity. Gravity is the only thing that's capable of doing work. And so if we're asking how fast is it going at the bottom, gravity is the only reason it's going faster at all. So the method so far actually is a much more broader ranging than you might think, because it accounts for gravity is one force and any other forces you might want, as long as they are only guiding forces. As long as they act 90 degrees to the motion, they will not have any bearing on the thing going faster or slower. So gravity and all guiding forces. Guiding forces are okay. So that's what we have. We have a problem. It's frictionless, so we don't have to worry about friction. We have gravity, which is definitely accounted for, and then we have normal force, which we basically get to throw in for free. All right? So think about it like this. If this thing fell off the side of the incline, and we asked for what's the speed here, it'd be the same answer. The fact that normal force guided one of these paths and was not present in the one that you fell straight down doesn't make a difference, because normal force would not make you go any faster or any slower anyway. Okay? So let's go ahead and tackle it. It's pretty much the same setup as the last one. It has no kinetic energy to start with because it starts at rest. It has no potential energy at the end because I'm going to set that to be 0. Same deal. All the energy initially is in potential. At the end, it's all kinetic. Dot, dot, dot. I get the same result. The only thing I need to do is figure out what's its initial height. This height right here. How much does it drop vertically? That is not handed to me on a silver platter, but I can easily get it from based on geometry. What is it? Is it 6 meters? How would I get it? 6 sine of 30, exactly. So the initial height here would be 6 sine of 30 meters. So if you plug that in, you should get a result of 7.7 meters per second. Does that seem shorter now than the old method? Seems like it to me. A couple lines still. Okay. So, it seems kind of strange to think that you'd reach a speed of 7.7 meters per second doing that and doing this. So this is another opportunity for me to talk to you about that one failing of the energy method, which is the time issue. Okay? So let me compare these two paths, this one and this one. They would not take the same amount of time, okay? If we looked at this in the old stuff, the size of the acceleration if you fell straight down is what? That's g, right? It would be like this, pointing this direction. If you were sliding down an incline, what was the acceleration size again there? You're welcome, have a good day. G sine theta. And of course points like this, and it's substantially smaller. So that's less than g alone, right? This has less acceleration. How is it possible that it can achieve the same speed at the end if it has less acceleration? There's got to be something to make up for that. What is it? distance, right? It has more distance and more time to do it. Less acceleration, but more distance and more time with it, so you can still have the same final speed. So don't get me wrong, this sliding down an incline will take a longer amount of time. They will not reach the bottom simultaneously. You will reach the bottom much earlier if you fall off the side of the incline than if you slide all the way down it. But what I'm saying is that once you do eventually slide down to the bottom, you will be going the same speed as if you fell off of it. In the extreme case, you could have an incline that's really, really, really shallow. But you're going to still reach the same speed by the time you get all the way down. All three of these have drastically different times of their motion, but energy tells us an insight that they will all be reaching the same speed by the time they get to the bottom. And the reason for that is that no